So this is just a video to go through some of the trickier questions from exercise 31.1, which we sort of, I suppose, maybe raced through the last day. So the three most difficult questions are probably 5, 8, and 10. I wouldn't be that concerned about 10. We hit on the next chapter again. So anyway, this one here is quite confusing. In 1919, Rutherford bombarded nitrogen with alpha particles. Now, in this scenario, the alpha particles are moving fast. They have a lot of kinetic energy. So what you'll find in this question, actually, that kinetic energy gets converted into mass, and you end up with the products being heavier than the reactants. And it was an important thing at the time. You have to be able to write that out if you're asked to do so. So the left-hand side are called the reactants, the right side are called the products, and there's a standard procedure to this style of question. You go and you work out the mass of the reactants, which are given in this case. So you work it out here. The mass of reactants, that's the nitrogen and the helium atom, the alpha particle. The mass of the products is the oxygen and the proton, or a hydrogen nucleus, if you like. So this number here is bigger, so therefore there's been a gain in mass. The energy you need to create this came from the kinetic energy of the alpha particle. Now, what was the gain in mass? Was that amount there? How much energy, therefore, would you need to create that gain in mass? You put that number there into E equals mc squared. Turns out to be that amount there. Now, what was the initial energy of the alpha particle? Well, we're going to convert this to joules here. 7.68 by 10 to the 6 is 7.688 mega electron volts. So you multiply that by 1.6 by 10 to the minus 19, and that's the energy of the incoming alpha particle. So now we take away the gain in mass, and we're left with, if you can read my bad writing here, 1.11531 by 10 to the minus 12. So this is the energy that would be given over to the products. So to the proton, and it says in the question that the proton gets 17/18 of the available kinetic energy, and this is the available kinetic energy. So we get 17/18 of that, and that's the energy of the proton. Pretty tricky question. And then to convert that into electron volts, which is the answer given in the back of your book, divide that by 1.6 by 10 to the minus 19, and you get 6.58 mega electron volts. Now, question 8 is a little bit easier, I think, but again, you need to be familiar with your maths tables. You have to go to your tables and find out what that's this cobalt 59, that's the mass number. What's the actual atomic number of cobalt 59? It's 27. And then a neutron enters its nucleus, so plus a neutron. So you add up the top and add up the bottom, you're still left your cobalt, but it becomes cobalt 60 with a gamma ray emitted. In this case, the reactants are heavier than the products, so we work out the difference again and convert that into energy, and that is the energy of the gamma ray photon. That's actually quite a nice question. And question 10, I did it out here, but again, I wouldn't worry about it too much as yet. Just to say, maybe, so you might try and get your head a small bit. You can work out the ratio of, there's a quick way of doing all this, you read all that much, but there's a shortcut. If the masses are in the ratio, for example, 60:1, then their speeds and their kinetic energies would have been the ratio 1:60. That saves you a lot of work there. And again, they kind of assume in the textbook that it's just a simple little simultaneous equation, but it's actually a pretty sophisticated one. If you want to, you can read through it there. It's going to be done in more detail in the next chapter in a shorter way, and we'll discuss that then. Okay, and good luck with that.